Hey, this is Amanpreet Singh, and today I'm going to talk about analog to digital converters. Up till now, we have been learning about digital audio and its processing, but now I'm going to have you take a step back and understand how the analog sounds in the real world are actually converted to digital signals to be processed. First, for those of you who do not have an electronic space, I'm going to explain the function of a few electronic components which are used in the circuits of analog to digital converters. The first component mostly used is a resistor. It is a two-terminal electrical component that provides electrical resistance. They are used for several things, and among them, the most common one is to reduce the current flow. The symbol for the resistance can be seen below, and it is usually denoted by R. Next comes the capacitor, which is used to store electric charge. In analog to digital converters, it is mostly used to hold some signal value for a brief amount of time. Moving on, many of you will be familiar with AND gate, which gives a high output or 1 when all its inputs are high and gives a low output or 0 otherwise. A 2-input AND gate can be seen on the left hand side, while its truth table is given on the right hand side. A comparator is used to compare two voltages or currents and gives an output indicating which is greater. As can be seen from the symbol, it has a positive and a negative input. If the positive input is higher, the output of the comparator is high or 1, and if negative input is higher, then the output is low or 0. Moving on, a counter, as its name suggests, counts. Mostly it is used to count the number of times an event has occurred. A 3-bit up counter made using toggle flip-flop is shown below. Here Q0, Q1, Q2 represent the 3-bit output of the circuit. However, the working of this circuit is not relevant to our discussion. Moving on, we have a decoder which converts every unique combination of input states to a specific combination of output states. A 2 to 4 decoder using 2 NOT gates and 4 AND gates can be seen in the figure below. The combination of input A1 and A0 is used to decide the output state, which can be either Y0, Y1, Y2 or Y3. Last but not the least, we have sample and hold circuit. This circuit is used to sample the given input signal and hold the sampled values until the input signal is sampled again. As can be observed, A1 and A2 are both operational amplifiers which are being used as a comparator, and CH is the capacitor, which is the central component of the circuit. The pulse below the circuit is applied to the switch to control the sampling and holding operation, while the input analog signal is applied at Vin. During the sampling time, which is represented by S in the switch input signal, the signal is turned on and the capacitor gets charged up to the input signal value. During the holding time, which is represented by H, the switch is turned off and the capacitor provides the output voltage until the beginning of the next sampling period. Moving on, as the name suggests, the analog to digital converters or ADCs are used to convert continuous time signal into its digital time representation. As can be seen below, the input of ADC is an analog signal and its output is a digital representation of the input signal. Now you might ask where we use these converters. We actually use them daily without even realizing. Whenever you make a phone call, these converters come into play. ADCs convert what you speak into digital signals and send it to the other mobile phone via modulation and demodulation. Now there are 3 steps in the conversion process of ADC. First is sampling, second quantization, third coding. All of these steps are performed in every ADC. First, sampling is the reduction of a continuous time signal to a discrete time signal. As you might all know, the sampling frequency is determined using Nyquist criteria, which says that the sampling frequency to be used should be at least twice of its base frequency. Now, if you are sampling at a frequency which is less than the Nyquist criteria, what you get is undersampling, which leads to aliasing effect. when you're sampling far above the Nyquist criteria, what you're doing is oversampling, which is intentionally used in modern analog to digital converters to help reduce the distortion which is introduced by practical digital to analog converters. Second is the quantization process. The signal can only take determined values which belong to a range of conversion based on the number of bit combinations that the converter can output. Now, since we are converting the analog signal to digital signal, there are bound to be some conversion errors, since the analog signal can take infinite number of values while we can only output a number of digital values. Those values are given by n is equal to the power n, where n is the number of bits of the analog to digital converter. Next process is coding. It simply means assigning a digital value to each sample. Now, the precision of ADC can be improved by either increasing the sampling rate or the resolution. Now, what this means is, when we increase the sampling rate, we are taking more samples per second, which increases the accuracy. When we increase the resolution, we are increasing the number of states that the output of ADC can take, hence again increasing the accuracy. Now, moving on to the types of ADCs that we are going to discuss. First, we are going to discuss dual slope converter, then the flash ADC, then successive approximation, and then sigma delta. Now, the circuit of integrating type dual slope ADC can be seen below. It uses two input voltages, unknown input VA and a reference voltage Vref, in addition to an integrator, a comparator, and binary counter. Now, the voltages VA and Vreference are always of opposite polarities, as indicated by negative in front of Vreference, since the operation of this ADC requires the nullification of the ramp generated by one voltage by the other. Initially, the counter and integrator are reset to 0, and the input of ramp generator or integrator is switched to unknown voltage VA. The analog input VA is integrated by the integrator and generates a negative ramp output. Hence, the output of comparator becomes positive and the clock pulse passes through the AND gate, which starts the binary counter. The ramp is continued for a fixed amount of time t1, which is counted by binary counter. After the counter reaches time t1, the value of binary counter is reset to 0, and the input is changed to the known reference voltage minus Vreference. The ramp now starts with a value minus Vs and increases in a positive direction until it reaches 0 volt, while the counter advances. When Vs becomes equal to 0 volt, the AND gate gets deactivated and the counter stops. The conversion cycle is now complete, and the amplitude of negative and positive ramp voltages can be equated to get the equation of input signal, which is VA is equal to minus Vreference into T1 by T2, which shows that the unknown analog input voltage VA is proportional to time T2, since Vreference is a known reference voltage and T1 is predetermined time period. The actual conversion of analog to digital takes place during the time T2. The amount of time it takes for the integrator's capacitor to discharge back to its original output voltage, as measured by the binary counter, becomes the digital output of the dual slope ADC circuit. This whole operation can be seen in the graph shown on the right side. Moving on, the advantages of this circuit is that the input signal is averaged, hence eliminating the need of sample and hold circuit. Moreover, greater noise immunity is provided as compared to other ADC types. In addition to that, it provides high accuracy. On the other hand, it is extremely slow and high precision external components are required to achieve that accuracy. Now, next is the flash ADC. This ADC and the other ADC architectures which we are going to discuss in a few minutes All capture the analog signal level at a single point in time every cycle, and if the input signal is noisy, these ADC techniques might convert a spike or a dip as they convert the signal repeatedly at a single point in time. This leads to the requirement of a sample and hold circuit, which was discussed earlier, to avoid this scenario. Moving on, Flash ADC is made by cascading wideband, low-gain, high-speed comparators, as can be seen in the figure. It shows an n-bit flash converter made using 2 to the power n minus 1 comparators and 2 to the power n resistors, which make up a resistive divider providing the reference voltage. The reference voltage of each comparator is one least significant bit less than the comparator immediately above it, so the reference voltage keeps on increasing as we move up. The comparator output is 1 when the applied analog input voltage is greater than the reference voltage. If the applied reference voltage is greater, then the output is 0. As can be observed in the figure, if the voltage of applied analog input is between voltage value of comparators x4 and x5, then the comparators x1 through x4 produce 1 as their output, while the remaining comparators generate 0 as their output. The point where the output changes from 1 to 0 is the point where input voltage becomes smaller in comparison to the reference voltage. The code is then decoded to an appropriate digital output value using the decoder. Hence, the conversion is complete. Moving on, Flash ADC has the advantage of being very fast and the simplest in terms of operational theory. However, as you might have noticed, it needs a lot of parts for it to work. Moreover, it has a lower resolution and is expensive. Next, we talk about Successive Approximation ADC. Its circuit diagram can be seen in the figure on the left hand side and can be considered the opposite of Flash type ADC. Since the Flash type ADC uses multiple comparators to perform the conversion in a single ADC cycle, the Successive Approximation ADC uses a single comparator over multiple cycles to perform the conversion. The ADC uses a sample and hold circuit to sample and hold the analog input voltage Vin. The binary algorithm used by Successive Approximation ADC is implemented by n bits SAR register, while DAC is a digital to analog converter which converts the SAR register value to an analog signal, which is used to compare using a comparator with the output of sample and hold circuit. Initially, the value of SAR register is set to mid value, that is, most significant bit of SAR register is made 1, while all the other bits are made 0. This value is then sent as input to DAC, which halves the value of reference voltage Vref getting applied to the comparator. The comparator will then compare the input voltage Vin with VDAC. If Vin is greater than VDAC, the comparator output will be set to 1 and the most significant bit of n-bit SAR register is retained for the next cycle. Else, if the Vin is less than VDAC, then the comparator output becomes equal to 0. The most significant bit of SAR register is also turned to 0 and the next bit is made 1 and comparison is performed again. This process continues till the least significant bit of SAR register is reached, and after that the output n-bit digital volt is available in SAR register. The operation of a 4-bit Successive Approximation ADC can be seen in the figure on the right. You can see how initially the reference voltage was higher than the analog input voltage, and then for the next comparison the voltage was reduced, then in the next comparison it was increased by a small amount until the value became equal to the analog input signal. Now moving on to its advantages and disadvantages. It is of medium accuracy and can attain high speeds for that accuracy. However, higher resolution successive approximation ADCs require going through a lot of cycles, hence the speed is very less for higher resolution applications. Moving on, we are going to discuss about sigma delta ADC, which takes a different approach when compared to other ADC architectures. Its basic form can be seen in the figure below, and it contains an integrator, a comparator, and a single bit DAC. The output of one bit DAC is subtracted from the input signal, and the resulting signal is integrated. The integrated output is then fed to the comparator and is compared with the ground voltage. The output of comparator is either 1 or 0 depending on the integrated signal. The resulting bit is given as input to DAC, whose output is again subtracted from input signal. This closed loop process is carried out at a very high oversampled rate. The digital output from ADC is a stream of ones and zeros, and the value of signal is proportional to the density of digital ones coming out of the comparator. This bit stream is then digitally filtered and decimated to result in a binary format output. This completes the conversion process of sigma delta ADC. Now, since sigma delta ADC uses oversampling, it has high resolution. However, due to the oversampling which is being used, the process is quite slow as it takes a lot of time to complete the sampling task. Now a comparison of all the ADC types that have been discussed so far has been presented by considering different parameters. However, we are going to focus on the first row, which tells you which ADC architecture you would need for what kind of application. As can be seen, the dual slope ADC is good when you need high resolution and low power consumption. However, flash ADC is the best when you're looking for ultra high speed when power consumption is not a concern, as it uses a lot of components for its use. Then comes the successive approximation, which is good for medium to high resolution, and it has a small size in contrast to flash ADC. However, the delta sigma has a high resolution and low to medium speed. Moreover, it doesn't require any external precision components. Now, with the discussion so far, you might have gotten the gist of how the analog to digital conversion takes place and which type of ADC you would need for what kind of application. So that concludes our discussion about analog to digital converters and how analog signals are converted to digital signals. Thanks a lot for listening. See ya.